We're set to begin a series of lectures now in our electric machine design course, a new set of lectures, and this set of lectures covers what's known as permanent magnet brushless DC motors, or by their new name, the most recent name, PMAC synchronous machines. These types of motors have been around since the early 60s basically because of the Apollo space program, number one, and number two, because the availability of high performance permanent magnets, namely the rare earths. And these early motors in the 60s were developed by Sperry Farragut and Kirchhoff. And Sperry Farragut used electronic commutation with photoelectric switches, emitting diodes and phototransistors to do the commutating, and Kirchhoff used Hall effect switches. Many companies over the years have developed products and brushless products using magnets, and as magnets and electronics improved over the next 20 years, along with the development of motors, things progressed to where they are today. By the 1980s, DC motors became the favored machine. Brushless DC motors became the most important motor for the emerging computer peripheral products like printers, tape drives, floppy disk hard drives, and later CD, DVD drives. It seems that in the 70s, IBM passed a law for the computer industry that thou shalt not use an AC motor inside of a computer or any of the computer peripherals. One of the main reasons for this was because AC motors their speeds controlled by frequency, and DC motors their speeds controlled by voltage, and different countries had different frequencies, so if they developed their products, they would have to have different number of poles in the motors for 50 hertz operation overseas or 60 in the United States, or if they didn't change the number of poles, they would have to change belt and gear ratios and things like that to get the speeds come out the same. So it was easy for them to use DC motors. They couldn't have brushes or commutators or slip rings because of life and because of noise, electronic noise that would glitch the logic. So brushes became popular. So by the 80s, that's the only machine that was used, and that included the cooling fans in the computers as well. They were all brushless. By the mid-90s, the names of the PMDC motor, BLDC motor, was changed to PMAC synchronous. They were the same motors. They were cousins of the DC brushless, but because they were powered with sine currents instead of DC voltages switched across the leads, they were powered by sine voltages and currents like AC induction motors, so the inverter people changed the name to PMAC synchronous motors. But a lot of people think the motors are different, but they're not really. There's a lot of versions have emerged since then: axial flux, slotless, and internal magnet versions, as well as the classical surface magnet versions. The shaft torque, again, just like other motors, is produced by the flux linkage from the permanent magnet, the rotor, with the flux from the permanent magnet rotor with the stator phase conductors. The speed is not really a true synchronous motor in the classical sense, in that it's a synchronous machine if you realize that it's a self-synchronous machine. It has to have knowledge to make it synchronize, to make it self-synchronous. The rotor, or the stator transistors have to have knowledge of where the rotor is, so that it will fire the right polarity of current to flow in the phases to properly link the flux from the rotating rotor. So it's self-synchronizing, and it doesn't have any slip. The rotor pole angle positions can be estimated pretty close, but classically they've been measured using some sort of a shaft-mounted encoder feedback, or the modern IPMs. You can calculate the rotor from the measured quadrature and direct axis inductances. For surface-mounted machines, these two inductors are almost the same, so it's very hard to discern where the rotor is from the inductance. Very high torque densities are very possible with these types of machines, as long as the number of poles are pretty high. The PM machine, as we've said before, is the closest you get for getting something for nothing in this world, because once you pay for the magnets and have them put in the motor, you get this field from the magnetic field from the magnets forever. Let's see. So another characteristic we've mentioned before is the number of poles in the stator don't have to equal the number of poles in the rotor like they do other machines. There's different versions of these. The axial flux versions can be configured with a rotor stator rotor on the shaft, or a stator rotor stator, or just a single rotor and a single stator. With where the plus signs are is where the axial flux travels. The transverse flux topologies can be single or dual gap. These are very complicated configurations, but very useful. The most common ones are radial flux machines, but of course there are linear versions of all these as well. The radial flux machine can have surface magnets. Here's the SPM, or internal magnets, the IPM. The surface magnet, all the torque is produced by the flux linkage of the magnets to the stator conductors. The IPM motor has two torque components. It has the torque component created by the flux linkage of the magnets, but it also has an additional torque component from the reluctance torque generated by the saliency of these poles in between the magnets. These are salient poles. So you could call the IPM a hybrid permanent magnet brushless, because it produces a reluctance torque and a magnet torque. Here's a very nice picture of an induction motor stator with half of it showing a proper 8-pole permanent magnet rotor, and the other half showing a proper 8-pole squirrel cage induction rotor. And as you can see, that the stators are identical here. The windings are identical. The axial flux machines have the variations we talked about before. Here's a rotor, stator, rotor. This is a Hall-back array type rotor with no iron. This backing, there's no back iron required for this. The only iron in this motor is the shaft and the bearings. This is carbon fiber backing plate, and this is the magnets that provide the Hall-back array, and there are carbon fiber spokes here to support this. And a 3-phase Litz wire winding configuration is what's in the stator here. Okay, there's obviously a bearing inside there, the shaft, and these things rotate together. This is another version here with a rotor, stator, rotor. Here's a version with a stator, rotor, stator, two stators. This is the easiest one to cool. It's easy to take heat off of the back of this. And this is another rotor, stator, rotor. This one isn't bad to cool either, because you have the end turns going over the OD, which could be in contact with an aluminum housing. This is what the Hall-back array looks like. This very interesting concept. You take high energy permanent magnets and you grind them or shape them in a mechanical direction that gives their magnetic direction in form of the arrows. So what you have is flux going this way, so you don't need back iron, and you can this is a 45 degrees, this is going outward, this is going tangentially 45 degrees and inward. So you basically create poles in the magnet like this. It's quite an interesting concept. There's a number of motor designs that operate on this basis. The drawback is the expense of making all these magnets. Now, the surface rotor configurations, here's an example of one with the magnets here. It's an 8-pole motor, I guess. And now here's a surface magnet with arcs. That's one choice, with saliency. Here's arcs with no On the outside, these are arcs on the outside. This looks like a DC motor, but it isn't. This thing here rotates, but it'll use magnets that look like the ones used in a permanent magnet DC motor. And this stator looks like an armature lamb. And so this is stationary, and this rotates. Here's some other versions of the same thing. Here's a inside rotor version. There's an outside rotor version, all the same diameters. These are the rotors that rotate, of course. And here's a bread loaf design. A bread loaf design kind of looks like a slice of bread, a funny looking slice of bread. But that's the shape. It's flat on one side and has the curvature and shaping on the outside. This is a radially magnetized. These are radially magnetized, and they're put together to form a complete ring. There's some interesting IPM configurations here. This is a spoke type. In other words, the magnets are slabs, and they're mounted inside of a rotor. This is a North Pole, South Pole, South Pole, North Pole, North Pole, South Pole, South Pole, North Pole. So the flux is focused, and this area plus that area is a lot greater than this area. So the ratio of those areas times the flux density of that magnet is the flux that you get pushing into the stator to link the conductors in the stator. Here's an 8-pole version. Here's an 8-pole version. This happens to be the Toyota Prius configuration, and the magnets are shaped in V's to have enough surface area to get enough flux, but they need these salient poles in between. So if this were straight across here, the magnet surface wouldn't be as great, so the flux would be less. So that's why you put it in a V. But this has saliency from the quadrature axis as compared to the D-axis. This is another version of that motor. Let's see, I believe this is the rotor that's in one of Ford Motor Company's hybrid vehicles. You can see the punch lamination held together with these dimples to stack, and then there's this little air passageways. These this is a little web that holds this thing together. That's a web that holds it together, and there's the neodymium magnets inserted into the slots. Here's a similar design. This is a small version of the type of rotor that Honda uses in some of their machines. They're IPMs too, but they don't have saliency. There's no steel in here. They intended this to be a surface magnet, but they fabricate it by punching the laminations so that it completely encases the lamb. That gives them magnet retention is what that does. So let's compare the IPM and the SPM. The surface machine has the highest torque density possible with permeance coefficients of 10 or more. That's the ratio of the magnet thickness to the air gap thickness. Highest torque to inertia ratio is possible, which is of any machine that is known. And I suppose that can be argued, but as far as I know, that's a true statement. And this is a very important characteristic for servo motors. Simple construction, but requires shaped arcs or breadloaf magnets. Highest torque linearity due to low leakage reactance of the surface magnets. Requires more magnet mass to resist demagnetizing fields. Limited constant power range due to field weakening difficulties. Many applications require with surface magnets require retention sleeves. The IPM motor consists of interior fitted permanent magnets inside a rotor core. There's an extra reluctance torque component provided from this configuration, so properly designed, the magnet mass can be reduced over an equivalent rotor for a surface mount design. Capabilities of 8 to 10 to 1 constant power ratio, which is very impressive. Magnet slabs are the lowest cost due to minimum grinding. They can be sliced and diced because they're rectangular slabs. Magnet retention is almost for free due to it being internal to the rotor laminations. Some leakage flux is present through the retention webs, but the retention is worth that loss, I guess. Rotor fabrication is somewhat more complex, but can be easily tooled and automated. Magnets can be thinner due to protection of being inside soft steel laminated poles for demagnetization. The control is more complex than surface, but can be justified by performance gains. This is a picture of the plot of the reluctance torque component. This is a reluctance torque component generated by the IPM, and it peaks at just the right place here, and this curve here is the alignment torque plot, and that alignment torque is the torque that's produced from the magnets. Now the peak torque occurs when the sum of these two components is maximum, which is determined by gamma, which is the current advance angle. And so you set that current's advance angle at a point where the sum of these two is maximum, and that gives you a torque component that is maximum. And this is very important because this is what gives you the wide constant power range and easy field weakening. So we'll study more about that later. But it's not. This doesn't indicate that much difference. But I mean, the reluctance torque is about well, it's not. It's about the peak reluctance torque here is only about 30% as much as the alignment torque, but it is. I have seen designs where it's 50-50. The stator requirement for these kind of machines is just like an induction motor, and it can be, you can use the same stator for either one. However, in selecting what kind of a stator you use, many times the cost dictates which one you're going to use. If you need real high slot fill, or if you have very high speed and a lot of poles, you've got high frequency losses. Special winding patterns and multiple phase connections have to be considered. Multiple phase means 2 3-phase circuits or 3-phase circuits, or special manufacturing reasons for cost of how you make the rotor, or how you fabricate the stator. But in principle, you can use an existing induction motor stator. Here's an example of a pole number versus torque density. As you can see, with 4 poles, you require a yoke this thick, just like in an induction motor. But if you go to 8 poles, and keep the OD the same, you only need half the thickness of the stator yoke. So the ID jumps from 150 millimeters to 132, and what that gives you is 2 things. That gives you a larger radius. So remember, torque is a moment of force. So if I generate a certain PSI in the air gap, I have a larger air gap, and if I develop the same force in the air gap, I get a lot higher torque density because the radius is different and the surface area is different. And of course, that the surface area is different relates. I got more flux in the machine as well. So here's some examples of stators with high slot fills. We've seen some of these before. This is a Ford stator. It looks like an induction motor stator. This is Ramey's stator. This uses rectangular wire, and you can. These are coils that are wrapped around a single tooth, like this centered set of parts here, and you can die form these and compress them and get very high density. So. This concludes this lecture. We'll go on to more topics with brushless motors in the subsequent ones. Thank you very much.